Hello, welcome to the course PH6B13E Computational Physics. The contents of today's lecture is taken from Numerical Methods for Scientists and Engineers by K. Shankar Rao. Today we will start fresh discussion on Module 3, Computational Approach in Physics. Numerical methods are very important for almost all branches of physics, particularly in the case of mechanics, because most of the problems in mechanics deal with equations of motion and the analysis of trajectory of motion. By solving the equation of motion using analytical methods, we are forced to neglect many parameters to avoid mathematical complexity. For example, if you consider a free fall under the action of gravity. So the equation of motion F equal to ma. F is the gravitational force, which is m into g. And if you are considering one-dimensional motion along the x-axis, then your acceleration is going to be d square x by dt square. So the equation of motion is mg equal to m into d square x by dt square. And most of the cases we take g as a constant, right? But we know that in reality g is not a constant. It varies as a function of height from the surface of Earth, right? But we don't consider that variation in our analysis. Why? If we consider that, our analysis is going to be more complex. So in order to simplify the analysis, we tend to omit these kind of complexities. Similarly, in many areas of physics, you consider non-interacting particles, especially in the case of metals. If you are trying to study the electronic properties, you will treat the electrons as free electron. Free electron means the electron-electron interactions are negligible. Actually, there are some interaction, but in your analysis, you are deliberately disregarding this interaction. Because once again, if you consider all those interactions, your analysis is going to be very tedious. So intentionally, you are forced to make a lot of omissions if you are following analytical methods. But in the case of numerical methods, that's not the case. You can include all the parameters because here you are solving a complex problem step by step, because at a time you are performing a little bit of calculation. If you recollect any of the numerical methods which we learned in the previous module, you can see that at the end everything boils down to addition, subtraction, multiplication, division, right? Various combinations of that in a repeated manner. So the actual calculation you are doing in a numerical technique is very simple, just that you are doing it repeatedly. So however complex is the problem, you can solve it numerically without omitting any parameters. So the fundamental idea behind numerical analysis is the concept of discretization. Discretization means splitting a continuous quantity into small discrete elements. So if you remember the numerical integration, so we have a huge range over which we need to perform integration. It's difficult to do the integral over the entire range at once. So what did we do? We divided the range into a number of small sub-elements. In each of the sub-element you did the integration and finally found the total value of the integral. So you divided the range into a number of small elements. So this is what is meant by discretization. Now when you are studying a physical problem, the physical quantity under study could be discrete or continuous. For example, if you are studying the motion of a simple pendulum, so here both the position as well as the time, both are continuous parameters. On the other hand, if you are studying the energy levels of an atom, the energy levels are discrete. So in real problem, the parameters could be discrete or continuous. But if you are solving the problem using a computer, the variable has to be discrete and finite. Computer cannot deal with continuous parameter. Similarly, a computer cannot deal with infinity. So all the parameters which we include in our numerical computation, they have to be discrete and finite. For example, to calculate the velocity of a body after tn seconds from the initial time t0, so what we do here, we divide the entire time range into a number of discrete time elements. So the original range is t0 to tn, you divide it into t0, t1, t2, t3, etc. So you make a number of elements. Each element has a step size h. So you can write t1 equal to t0 plus h, t2 equal to t1 plus h, or in terms of t0 you can write it as t0 plus 2h, t3 is going to be t0 plus 3h, similarly tn is t0 plus n. So you divide the continuous range into a number of discrete elements. Now you can calculate velocity at each of the time interval. So your original idea is to find velocity at tn. You cannot calculate it directly, so you calculate at each subinterval, and step by step you finally arrive at the final solution. So this is the idea behind discretization. Now let's see how to find position and velocity of a body following Euler's method. We know that acceleration a equal to delta v by delta t, or delta v equal to delta t into a. And we know that the time interval or time step is nothing but the step size h. So I can write delta v equal to h into a. So in the first subinterval, delta v is nothing but v2 minus v1, which is equal to h into the corresponding acceleration a1. So a1 is the acceleration in the first subinterval. From this I can write v2 equal to v1 plus h into a1. Same way, in the second subinterval I can write v3 minus v2 equal to h into a2. Now if you follow the same procedure, you get v3 equal to v2 plus h into a2. So this is the general form of the equation. You can write vi plus 1 equal to vi plus h into ai. So vi plus 1 is the new value of the velocity. Vi is the value of velocity in the previous subinterval, or this is the old value. H is the step size. Acceleration is nothing but the derivative of velocity, right? And derivative is the slope. So once again, you are using the Euler's formula, new value equal to old value plus slope into step size. So this is how you calculate velocity of a body using the method of discretization. Same way you can also calculate the position. Follow the same procedure. Velocity is delta x by delta t. Here we assume that motion is one dimension along the x-axis, and delta t is h, so v equal to delta x by delta h, or delta x equal to h into v. In the first subinterval I can write x2 minus x1 equal to h into v1, or x2 equal to x1 plus hv1. In the second subinterval, this is going to be x3 equal to x2 plus hv2. In general, xi plus 1 equal to xi plus h into vi. Once again, the new value of position equal to old value plus slope into step size. So what we are doing here, we divide the total time into small elements. From the initial value, find the velocity and position during that particular element. And using that value, you can find velocity and position in the next time element. So this is continued to the last time slot to get the final value. Now let's apply this technique to find position and velocity of a freely falling body. So as you know, a body is freely falling only under the influence of gravitational force. So its acceleration is going to be the acceleration due to gravity. Actually, there are other forces acting on the body. There are other parameters we have to take into account. For example, as I said, the variation of acceleration due to gravity. Then you have the force of buoyancy, the viscous force, air drag, etc. But for simplification, we are not considering all this. We assume that the body is falling freely under the influence of gravity alone. So in this scenario, the acceleration of the body at any point is going to be the acceleration due to gravity, which is 9.8 meter per second square. So the body has a constant acceleration. Now what you have to do? You have to divide the entire time into a number of discrete elements of width h. Then using Euler's equation, you can write Vi plus 1 equal to Vi plus h into Ai, and Xi plus 1 equal to Xi plus h into Vi. So you will be given the initial values of position and velocity. So that's going to be position and velocity in the first element. Now in the case of a freely falling body, the initial velocity is going to be 0, and you can also assume that you can also take the starting point as the 0th point. Okay, so initial position is 0, initial velocity is 0. And using these values, you can calculate position and velocity in the next element, and you repeat it finally and get the final solution. Let's do a quick problem. The body is freely falling from a height under the influence of gravity, and the velocity and position at the end of 1 second. Tabulate the values at an interval of 0.25 seconds. So initial position is 0, initial velocity is 0, and time duration is 1 second, time step is 0.25 seconds. So we know the equations. Vi plus 1 equal to Vi plus h into Ai, Xi plus 1 equal to Xi plus h into Va. So step 1 in the first subinterval. So in the first subinterval, velocity is the initial velocity 0, position is the initial position 0, and the acceleration is constant, which is 9.8 meter per second square. Now in the second subinterval, so the step size is 0.25, so you are calculating velocity at 0.25 seconds. So this is V of 0.25. This is equal to Vi, which is V0, plus step size h into Ai. And Ai is a constant value, which is 9.8. So this is 0 plus 0.25 into 9.8, which is 2.45. Now x of 0.25, after 0.25 second, what is the position? This is equal to x0, which is 0, plus step size, which is 0.25 into Vi. Vi is the value of the velocity in the previous element. So the previous element value is V0. V0 is 0, so you get x of 0.25 equal to 0. So sometimes people write this value of velocity here, V of 0.25 here. Don't do that, because in every calculation you are taking values from the previous element. So this has to be V0 here. Now in the third subinterval, so you have to find velocity after 0.5 second and position after 0.5 second. So V of 0.5 equal to V of 0.25, which is 2.45, plus step size into acceleration. X of 0.5 equal to X of 0.25, which is 0, plus step size into velocity in the previous step, that is 2.45. So you get the position and velocity. Same way you find velocity and position after 0.75 seconds and finally after 1 second. Right? So you are arriving at the final solution step by step. So this is the meaning of discretization. Now if you look at the tabulated value, so you have time 0, 0.25, 0.5, 0.75 and 1, and the corresponding velocities here. Now if you look at this particular value, this is physically meaningless because you start with 0 velocity at position 0. After some time you have velocity 2.45, but the position still remains 0. And this doesn't make sense, right? Because your object has a certain velocity, but the position hasn't changed, right? Because a body can acquire velocity only if there is a change in position, right? So this is the error associated with numerical method, and this is kind of inevitable. It's going to be there always. So in numerical techniques, in the first step, there is going to be some error, but you can see that in the subsequent steps, the error gets compensated. Now, you cannot avoid it, but you can decrease this error. So you can see that here step size is quite large, 0.25 seconds. So what you can do is you can reduce the step size because the error is going to be large only in the first step. So when you reduce the step size, the weightage of the error is going to decrease, right? And as I said, in each step, in each subsequent step, the error is going to get compensated. When you reduce the step size, what happens? Number of iterations increases, number of steps increases, right? So the error is going to get more compensated. So that's one technique you can do, but remember that this you cannot avoid this, right? This is inherent in numerical techniques. And finally, how to do this program using Python platform. So the program is very simple. We have basically 4 parameters: initial position and velocity. You call that as x and v. Then you need to know the final time and the step size. So I input all these parameters using the split function. So I input 2 parameters at a time. I might as well input all 4 of them at once, but this line is going to be very lengthy in that case. So that's why I split it into 2. So it's your choice. Or if you want, you can input 1 at a time. And in this particular case, acceleration is a constant. So instead of inputting it from the user end, I directly define as a equal to 9.8 and the initial time t equal to 0. Then you print the titles of the table: time, velocity, position, and the initial values are readily available, so you can straight away print them. So the initial value of t, v, and x are printed. So in this table, the first row is ready. Now you need to print the second row onwards. So basically you need to move to the second element. So I increment time by the step size h, t equal to t plus h. To perform the iteration, I invoke the while loop, and the condition is t less than or equal to the final time tf. And inside the loop, I straight away write the equations: x equal to x plus v into h, v equal to v plus a into h. So the position and velocities are modified. Then you print the values. Then you increment time by step size. So once this condition is met, the iteration will stop, then you end the program. The one thing you have to particularly keep in mind, you should follow this particular order: the position equation first, followed by the velocity equation. Why? Because in the position equation you have a velocity term, right? And this velocity is the velocity in the previous interval, in the previous step. So if you write the velocity equation first, your velocity gets modified. Your velocity is going to be velocity in the current step. And when you do this step after that, in this case, the velocity is not the old value, it's the new value, it's the modified value. But that's not what we want. We want velocity from the previous step. So always write the position equation first, then the velocity equation. So that's for today. Thank you.